Hey everyone, welcome to this explainer. I am absolutely thrilled you're here with us today, because today we are going to decode something that's practically invisible, yet absolutely essential. We're looking at the meticulously calculated mathematical blueprints that connect literally our entire digital world. It's a really fascinating journey into the architecture of connectivity, and I can't wait to share it with you.
So, have you ever actually stopped and wondered how all the devices in your office or your school, or even just your favorite coffee shop, seem to magically talk to each other? You plug a cable in or you log onto the Wi-Fi, and suddenly, boom, you have the entire world right at your fingertips. Well, I promise you, it is absolutely not magic. It is a highly deliberate, meticulously planned physical and logical design.
Okay, let's dive into this. The whole idea of deliberately designing a network layout, it actually goes way back. Picture this. It's October 1969. Engineers working on ARPANET, which is essentially the internet's granddaddy, realized that just randomly connecting network nodes was incredibly inefficient. So, by applying formal mathematical principles to redesign the network's layout, they made the whole thing 25% cheaper to run and delivered 40% higher throughput. And here's the kicker. They didn't even change the underlying technology. They literally just changed the shape of the network. That proves exactly how much your network layout really matters.
To truly understand how we got from ARPANET to today's totally seamless connectivity, here is our roadmap for the explainer. We'll cover the blueprint of connectivity, network scales from PAN to WAN, the topology evolution, the star topology champion, logical versus physical layouts, and finally, scaling up with hybrid networks. It's a really logical progression, so stick with me.
All right, let's kick things off with Section 1, the blueprint of connectivity.
The technical term for what we're talking about here is network topology. Think of it as the invisible blueprint that dictates exactly how nodes, your computers, routers, switches, are arranged physically, as well as the logical path that data takes to actually communicate. It is exactly like an architectural plan for a skyscraper. A super solid foundation and a smart layout are absolutely essential to make sure everything built on top of it remains stable, efficient, and most importantly, ready for future expansion. Moving right along, we have Section 2, Network Scales, from PAN to WAN. Before we get into shapes, we have to grasp the sheer scale of these things.
And this brilliantly illustrates how networks expand so massively in scope. We start at the smallest level, with the PAN, the Personal Area Network. This is tiny, under 10 meters. Think of your Bluetooth earbuds connecting to your phone in your pocket. From there, it scales up to the LAN, the Local Area Network, which connects an entire office building or a school campus, up to around 2 kilometers. Then, we jump up to the MAN, the Metropolitan Area Network, spanning up to 50 kilometers, usually using high-speed fiber to connect, say, city government buildings. And finally, we hit the WAN, the Wide Area Network. This spans across whole countries and continents. The internet itself is literally the ultimate global WAN. It's just wild to think about the physical infrastructure required at every single step of that scale.
All right, Section 3, the topology evolution. Let's look at how the shapes of these networks had to adapt over time.
Tracing this history is actually pretty funny, because early networks were, frankly, a bit of a chaotic mess. We saw the 1969 ARPANET redesign, sure, but then in 1973, the original Ethernet rolled out using what we call a bus topology. Fast forward to the 1990s, we were connecting enterprises over shared WANs. And then, by the 2000s, a completely new champion emerged, the star topology. But to really appreciate why the star took over the world, we kind of have to look at what went so disastrously wrong with the bus layout.
So, early Ethernet relied heavily on this bus topology. It basically utilized a single shared cable. I want you to think of it like a single main street running straight through a small town. Every single device is hooked up to this one main road. The huge conflict here is what we call a shared collision domain. If multiple devices decide to transmit data at the exact same millisecond, those electrical signals overlap. The data packets quite literally crash into each other right there on the wire, corrupting the whole transmission.
So, to survive these constant, annoying collisions, early networks had to use a protocol called CSMA/CD. It essentially forced a strict listen before you talk rule. A computer would literally listen to the line for existing electrical signals. If it was totally quiet, okay, it would transmit. But if it detected a voltage spike, meaning a collision just happened, it would immediately stop, send out a high-frequency jam signal to warn everyone else, and then wait a totally random amount of time before trying again. It's a clever workaround, right? But as networks grew and added more devices, this became incredibly inefficient. Too many devices basically meant a permanent Main Street traffic jam.
Which brings us to our hero, Section 4, the star topology champion.
Look at this absolutely massive statistic. Today, a staggering 99.5% of business local area networks use the star topology. It didn't just compete, it absolutely conquered modern connectivity. So why was it such a game changer?
So the crucial point is how it physically routes the data. Think of the star solution like a major airport hub. Instead of everyone sharing that single main street, every single computer, every printer, every server gets its own dedicated point-to-point cable connecting directly to a central switch. This brilliantly isolates the traffic. You are no longer sharing the wire with your neighbor, which means, you guessed it, no more collisions.
Here is exactly why the star topology completely dominates the industry. First up, fault isolation. If one cable gets accidentally cut or chewed by a rat, only that single connected device goes offline. The rest of the network keeps humming along perfectly. Second, scalability. You want to add a new employee's desk? Just plug a new cable into an open port on the switch. Easy. Third is centralized management. Your IT team can just sit at the switch and monitor the health of the entire network. And finally, security. Because all traffic is forced to flow through the center, administrators can easily segment departments and enforce super strict access controls.
Okay, Section 5, Logical versus Physical Layouts. Brace yourself, because there's a bit of a plot twist here.
Now, what's really interesting about this slide is this massive caveat. Physical layout does not always dictate logical behavior. What do I mean by that? Well, just because your cables are arranged in a beautiful star shape, radiating out perfectly from a center point, it actually does not guarantee that the data flows that way underneath.
Let me show you the stark difference between the devices sitting at the center of that star. If you use an older, unintelligent device called a hub, it takes incoming data and just blindly broadcasts it out to every single device connected to it. So it physically looks like a star, sure, but logically, it acts exactly like that old shared Main Street bus topology, bringing all those nasty traffic jams right back. A modern switch, on the other hand, is highly intelligent. It reads the specific MAC address of the data and uses what we call unicast to deliver it only to the intended recipient port. The switch is the actual brains that makes the star topology function flawlessly.
And hey, we definitely can't forget about wireless. Wi-Fi is technically speaking a star topology, with your router acting as that central point. But here's the catch. Because all your wireless devices share the invisible radio spectrum through the air, it's essentially a shared medium all over again. So wireless networks have to use a protocol called CSMA/CA, which stands for collision avoidance. Devices actually have to send a request to send and wait for a clear to send from the router. They are literally coordinating their invisible flights through the air to avoid crashing into each other.
Which brings us to our final section. Section 6, Scaling Up, Hybrid Networks. How do we take this to an enterprise level?
Let's move to this setup and see how this builds outward for massive enterprises. You build what's called an extended star or a tree topology. Because obviously you can't just plug 10,000 devices into one single switch, right? So you build a star of stars. You put an access switch on every single floor of a building, each creating its own local star network. And then you connect all of those switches upward to a massive, incredibly fast central core switch. This creates a brilliant, totally fault-tolerant hierarchy that can easily cover entire university campuses.
And by mixing these layouts and layering on some smart software, organizations can do some truly incredible things. In healthcare, hospitals use this topology to heavily prioritize life-saving real-time heart monitor data over, say, a nurse downloading a large PDF. In retail, they use it to securely segment their guest Wi-Fi portal completely away from their sensitive point-of-sale cash registers. And in big corporate spaces with bring-your-own-device policies, they use tools like IPSK to issue a completely unique Wi-Fi password to every single user, tightly securing a massive, otherwise shared network.
But before we wrap up, I do want to introduce one very modern alternative layout, the mesh topology. For sprawling outdoor areas where running physical cables is just impossible, wireless mesh devices don't just connect back to one single central hub. Instead, they connect to multiple neighbors simultaneously. If one single node drops out or loses power, the data instantly, intelligently finds a new route. It creates this highly resilient, totally self-healing web of pathways.
Which leaves us with this final, somewhat provocative thought.
We rely on the trusty, centralized star topology for almost everything today. But as billions, literally billions, of new Internet of Things devices come online over the next decade, from smart streetlights to autonomous factory sensors, will the traditional star topology be able to handle that sheer density? Or is a decentralized, self-healing, mesh-driven future completely inevitable? Thank you so much for joining me on this explainer. Next time you connect to a network, take just a second to picture those invisible blueprints making it all possible. Keep learning, and I will see you next time.